and welcome to my virtual classroom. I am Jalaram, currently working as a lecturer in QAS College of Pharmacy, Ongole, Andhra Pradesh. So the COVID-19 has given a very tough and difficult situation for us, disturbing our normal routines. As an effort to adapt to the new normal, the lecturers are now shifting towards online platforms, taking online classes. So this is my small effort to reach out to the students in delivering the contents of the subjects. And the topic for today's class is rheology. The contents that we are going to see in today's class will be as follows. Introduction, which deals with the terminologies used in rheology. Then application of rheology in pharmacy, followed by classifications of different dosage forms on the basis of rheological properties as Newtonian systems and non-Newtonian systems. Always I recommend and I do give some inputs and historical background data about the topic which I am going to take. This is just to brief the students to know what happened and how this particular topic evolved, what is the need for the topics to come, and why I am reading the topic in pharmacy. So these things are very important, which changes the perception, which changes the way the student sees the topic. So maybe most of the students are not that much interested in history because it doesn't give you any marks, but we should accept that historical data is also important and it also carries some values. Right. Now we'll talk about rheology. Rheology, yes, as you all know, it's a science. It's a branch of physics. Exactly to say, it's a branch of physics. Came into existence in 1929, and the pioneers of this particular branch of physics are Marcus Rayner and Eugene Benka. So they coined the term as rheology, and that particular branch of study is going to deal with flow of liquids, semi-solids, and solids, and probably deformation of solids. Interestingly, this particular rheology was more prominently used in food and paint industry during early 1920s. It was an era of mass production. So from small scale productions, big factories were constructed where everything is produced in a very large scale. So in that way, we can say that example of food industry, ketchups and chocolates, they are produced in large numbers, paints. So they had a difficulty in the preparation or production cycle, especially in terms of quality control. The ketchups are very viscous, and paint is also emulsion. Paint is nothing but an emulsion, right? So colored pigments, oily pigment dispersed in water. So we have a very big challenge in the evaluation of the quality. So there was a batch-to-batch variations. There was no particular endpoint to check the consistency and the smoothness of the formulation. It was decided based on the opinion of the experts. So there was a big variations from batch to batch. One person feels that the consistency is good, whereas another person feels that it is not good. In order to remove that ambiguities, they want to have a logical and scientific way of assessing or evaluating the consistency and smoothness. That type this rheology came into the picture. They started to use the principles, equations, and all the theories of rheology applied on that particular product to quantify in a more logical way that this is the correct consistency. So later on, seeing the success of that thing, George W. William Scott Blair applied the principles of rheology for the pharmaceutical dosage forms also, because pharmaceutical dosage forms also similar to ketchups and paints, right? So they are also emulsions and suspensions. So we do have the same type of formulations in the pharmaceuticals also. So he was called as the first rheologist who used the scientific principles of rheology in pharmacy. That's the way rheology came into pharmaceutical field. Right. So before going to the depth of rheology, we need to understand certain basic concepts. Uh, Concepts from solid mechanics, fluid mechanics, right? I am not going to disturb you much with very big scientific details. I am just giving a very common, very simple way of understanding. Here in rheology, we are going to take an object, whatever the object or a system we have to study, we have to take that our point of interest, right? Take that, apply stress. Okay. So stress is nothing but a force per unit area. So on applying that particular stress, the particular object will start to give some response. So the type of response given by the object is called as strain. So basically we are going to have two things. One is stress, the other one is strain. So whenever a pharmaceutical system, right, maybe emulsion, suspension, creams, anything is subjected to a stress, it will show some strain. So stress is the force applied and strain is the response by the object. The strain or the response may be showing some changes in mechanical properties or rheological properties. And the changes may be elastic or plastic. So elastic means the changes gets reversed. So when you apply the stress, the change happens. When you remove the stress, the change comes back to normal. That is elastic. Plastic means once you apply the stress, it undergoes some change. After removing the stress, the change doesn't come back to normal. We call that as plastic, right? So in particular with rheology, we are going to be concerned about the stress, namely shear stress. So now there are two types of stress that are available. Generally, they are called as tensile stress and shear stress. So tensile stress is the force which is acting perpendicular to the object, and shear stress is the force which is acting parallel to the object. So the difference between tensile stress and shear stress depends upon the direction at which the particular force is applied. Okay. Next important thing or terminology in rheology is rheogram. So rheogram is a curve or a graph which shows the relationship between shearing stress and shear rate. So here shear rate is the strain. Okay. The response of the object after applying the stress is called as shear rate. So rheogram is very important to study the rheological property of any object, and rheogram is nothing but a curve which relates shearing stress and shear rate. Okay, right? So stress, strain, and rheogram. These are the things which we need to make it clear. Okay, and again under stress it is shear stress. So let me give a detailed explanation about tensile stress and shear stress. Yes, as I said, tensile stress or normal stress is the force acting perpendicular to the object. You can see here there is an object, a solid object, and the force is acting perpendicular to the object. And because of force, you can see that solid has compressed. So the strain is developed. It is shown in the form of compression. Sometimes the solid may elongate, right? So the compression or elongation is the strain, okay? And the force is the stress. This is tensile stress, okay? And it's generally observed that the tensile stress is directly proportional to strain, okay? Now we'll take the example of our point of interest, shear stress. So shear stress is the force is applied parallel to the object. So you take the object here, now the force is applied sideways, tangential or parallel to the object. Okay, and because of this, it is experiencing some sliding motion. So whatever the strain that is caused because of this shear stress is called as shear rate. Okay, so like tensile stress, here also the shear stress is directly proportional to strain. So more the stress, more the strain. Okay. Right. Why rheology is applicable for pharmacy? So rheology or rheological properties are very important in many aspects. So right from solids, semi-solids, liquids, everywhere rheology is important. For example, if you take fluids, right, mixing of fluids is affected by the rheological property or viscous. Simply we say that it's viscosity. So viscosity of the liquid is very important when you are going to mix two liquids, right? Then viscosity becomes important for dispersed systems also, right? Transferring of liquid from one place to another place through pipes, pumping the fluids through the pipes. Okay, stability of dispersed systems, right? And passage of fluids from one container to another container, or removal of suspensions or solutions from the bottle, dispensing the medicament from the bottle to the dispenser. All these things are depend upon the rheological properties of viscosity. In case of semi-solids, spreading of semi-solids like creams, ointments, spreading of ointments, creams, sticking of the ointments to the skin, right? Removal from the jars, release of drugs from the semi-solids, all are depend upon the viscous nature or the rheological property of the substance, right? Solids. When it comes to the solids, flow properties of solids all depend upon the rheological properties. Okay, the type of equipment used for mixing and the capacity, production capacity of the equipment, all these things are depend upon the rheological property of the substance. That's the reason why rheology became important in pharmacy. Right, next comes to the important picture here, classification of substance based on rheology. There is basically two classifications, Newtonian systems and non-Newtonian systems. As the name says, Newtonian system means any system or object which obeys Newton's law of flow. Non-Newtonian system means it does not obey Newton's law of flow. Now we have to know what is Newton's law of flow, right? So Newton's law of flow is defined as at any given temperature, the shearing stress is directly proportional to shear rate. It's a very simple law, nothing big complications. At any given temperature, shearing stress is directly proportional to shear rate. So now we know the meaning of all these terms. Shearing stress, what is that? The force acting parallel to the surface. And what is shear rate? The changes that happen due to the shear stress. Now, if the stress and the strain are directly proportional, then we say that the particular object obeys Newton's law of flow. Then it is called as Newtonian system. Okay. Now, how to know that the particular object is a Newtonian system? Right. For that, rheograms comes to our help. Okay. So recollect that rheogram is a graph which gives relation between shearing stress and rate of shear. Okay. So we have many modern viscometers many modern instruments which can measure shearing stress and the rate of shear. Okay, just take the object which is under study, put it into the viscometer, right? You can measure the shear stress and rate of shear. You can change the rate of shear or you can change the shear stress depending upon the design and the uh, principle of the instruments. You can measure shearing stress as well as rate of shear. So take the values and plot it in the graph. Right, so Rheogram is a graph which relates shearing stress and rate of shear. So whatever the values we get from the viscometer, we can directly plot it in the graph and we'll get a Rheogram. Now based on the graph, we can interpret it whether it is belongs to Newtonian or non-Newtonian. If it is a non-Newtonian, whether it is plastic, pseudoplastic or dilator. As simple as it. Okay. Right, now this is a rheogram for a substance which obeys Newton's law of flow. Right, so we have to first interpret the graph or what the graph looks like. Right, it's a straight line. Okay, so rheogram has a straight line. What does it mean? It means that shearing stress and shear rate are directly proportional. They are directly proportional. Right, so that is the Newton's law. Newton's law clearly says that shear stress should be directly proportional to the shear rate. So if it is directly proportional, then we will get a rheogram which is having a straight line. Okay. So when you get a straight line, what does it mean? So whenever there is a change in the rate of shear, for example, 10% of the rate of shear is changed or shear rate is changed, there will be consequently 10% change in the shearing stress. Likewise, if we increase the shearing stress by 25%, it will produce a consequent 25% of change in the shear rate, so that at any point the ratio is same. Okay, so at any point the value is going to be same or it's going to be a constant. So Newtonian systems can be defined by a single value. It can be defined by a single value, right? So the value will not change when you are changing the stress or the rate of shear. Okay, so Newtonian systems will have a single value to define, right? Second, the line passes through the origin. Okay, the line passes through the origin, 0, 0 origin. It means that the change are spontaneous. The change are spontaneous. For example, when you change the rate of shear or change the rate of shear stress, it starts giving the change immediately. Okay, the flow is spontaneous. Okay, so the Newtonian systems are defined by a single value and the change is spontaneous. These are two important things, right? So let us go into the depth of detailed, elaborate explanation for a Newtonian system. So for example, you take a Newtonian system and this is a very small block of a Newtonian system, a liquid which is acting as a Newtonian system. When you take that liquid, okay, the liquid is resembling a deck of playing cards. Okay, so like a playing card, how it is arranged one above the other. The liquids are also arranged as one layer of liquid molecules and is arranged over another layer of liquid. These are the layers of liquid molecules arranged one over the other as a playing cards. Okay. Now, when this particular liquid is subject to shearing stress, the shearing stress is applying force parallel. So this is F denotes the shearing stress. When that shearing stress is applied, it causes some change. What is the change here? The layers of the liquid starts to move. We know that whenever stress is applied, the object will show some strain. Here, the strain is moving of liquid layers. Okay. So once the force F is applied, the layer starts to move. Okay, the layers start to move, right? And the movement of the layers, movement of the liquid molecules depends upon the stress. Okay, more the stress, more the movement. Clear? Now, so when you see that rate of speed or rate of velocity or the rate of the speed at which the layers are moving or velocity, we see that not all layers are moving at the same velocity. The rate of speed or the velocity of the layers are not uniform. Okay, the layers which are on the upper layer, or the layers which are on the topmost portion, they are moving very fast when compared to the layers which are at the bottom. You can see here almost the bottom layer is stationary, it did not even move. The topmost layer has moved to a large extent. So this is the distance traveled by the first layer, and the bottom layer did not move at all. So it's very clear that there is a difference in the velocity of the layers. Okay, this difference in the velocity generates a gradient. So gradient is a state where there is difference in the parameters. Okay, so velocity gradient. So here we say is velocity gradient. That means in one part the velocity is more and another part the velocity is less. So it creates a velocity gradient. So how this velocity gradient is created? Due to the force that we applied. So F is the shearing stress that has caused a velocity gradient. Okay. Now we have to quantify the velocity gradient. So velocity gradient is quantified as dV, difference in the velocity, by dr. So what is dr? Distance from the bottom layer. So the speed at which the layer is moving is depend upon the distance from the bottom layer. If the distance is very small, velocity is less. If the distance from the bottom is very high, the velocity is more. The velocity gradient is quantified as dV by dr. Okay. Now dV by dr is the effect of the force F applied to the liquid, right? So stress and strain both are quantified. So what is the stress here? F. And what is the strain here? dV by dr. So dV by dr is nothing but velocity gradient. In our rheological term, it's called as shear rate. Okay. Then, as per Newtonian law, shear stress is directly proportional to shear rate. What is the shear stress here? F. And what is the shear rate here? G. So F is proportionate to G. In order to remove the proportionate sign, we have to introduce a constant. That constant is coefficient of viscosity. Right? So viscosity is going to be a measurable quantity to know the movement of the layers. Right? So more the viscosity, lesser the movement. So it is called as a measurement of internal resistance. So eta is the coefficient of viscosity, which is quantified as eta equals to F by G, where F is the shear stress, shearing stress, and G is the shear rate. Okay. So Newtonian systems are clearly studied by measuring viscosity. Okay. And viscosity, different types of viscosity are there: kinetic viscosity, then absolute viscosity, intrinsic viscosity, everything, right? Okay, so Newtonian law, rheogram is a straight line. It means that shearing stress and shearing rate or shear rate are directly proportional. A single value is enough to define the whole thing, and it does not change on changing the shearing stress or rate of shear, and that single value is called as coefficient of viscosity. It is given by the formula eta equals to F by G and measured in points. Okay, right. So not all systems are so good like Newtonian systems. Okay, so many and most of the objects do not obey the Newton's law of flow. So we call those systems as non-Newtonian systems. So non-Newtonian systems are studied in detail by B.pharm. So we call them as B.pharm bodies. Okay. So non-Newtonian systems are subclassified into plastic system, pseudoplastic system, and dilatant system. Right. And these do not obey the Newton's law of flow. Now we go to the explanation of plastic system. So this is the rheogram of plastic system. Yes, you can see here shearing stress is plotted against rate of shear, and it gives a different picture here, curve as well as a straight line. So it's not a straight line. So it is not a straight line. What does it mean? Shearing stress is not directly proportional to rate of shear. Of course, it is not, because if it is directly proportional, then it becomes Newtonian, right? So from the diagram, we can understand that shearing stress is not directly proportional to rate of shear. Okay. Second, it does not pass through the origin. Yes, it is not passing through the origin. So what does it mean? The changes are not spontaneous. Changes are not spontaneous. Okay. So let's start interpreting the rheogram in detail. So this is the origin. When I start applying the shearing stress, for example, I have taken this one object and put it in the viscometer. Now I am changing the shearing stress. Okay. So once I started shearing the stress, increasing the shearing stress, there is no change. There is no change in the system, right? Now up to this point, no change, right? Shearing stress, it starts to show some change from this point, but it is not a straight line. Okay, it is not a straight line. Then after this particular point, whatever the change happens in the shearing stress, corresponding and equal change is happening in the rate of shear. So that means it becomes a straight line. Straight line denotes shearing stress and rate of shear are directly proportional. So it becomes directly proportional from the above this point. Okay, this point is called as yield value. This is called as yield value. Okay, right. So this rheogram for plastic system is giving some inputs for us. First thing is it's not a straight line. It becomes a straight line beyond yield value. So above yield value, the curve is a straight line. Below that yield value, it is not a straight line. Second thing, the flow, the changes are not spontaneous. Okay, so now we'll apply all these things in an example. You can understand it better. So plastic system example is 10 to 30% of flock-lated suspension. So flock-lated suspension is also a known topic to you. Flocks are nothing but a small aggregation of particles. They are made into a aggregation by weak van der Waals forces of attraction. They have three-dimensional attract force which helps up the molecules. You can see here this is a flock. Okay, so you can see 1, 2, 3, 4, 5, 5 particles are attracted or forms aggregate by weak van der Waals force of attraction. So this is what happening in the flock-lated suspension. So we know that by the formation of flocks, the particles settles quickly, but they do not form a hard cake. When applying a stress, it redistributes easily, right? So that is the flock-lated suspension. So flock-lated suspension is the best example for plastic system. So what's happening here? So when you take a flock-lated suspension and put it in the viscometer and start applying the stress, you see here up to the yield value, right? Up to the yield value, there is no change, there is no flow. Okay. Beyond the yield value, flow starts. Okay. The change is what here? Reduction in viscosity, and the flow starts. Now we need to explain why it happens like this. Okay. Why it happens is yield value or the stress corresponding to the yield value is consumed by these flocks. It is consumed by these flocks, and this flocks deaggregates or it splits into individual particles. Once it splits into individual particles, it responds to the stress and starts to flow immediately, and that change is directly proportional. Okay, so what's happening is initially we have the flocks. When you apply the stress, some amount of stress is consumed by the flocks to deaggregate or split into individual particles. That value or that stress is equal to yield value. Yield value is nothing but the stress required to break the flocks into individual particles. Once the individual particles are formed, like Newtonian system, it starts to flow. The change applied is directly proportional. Okay, whatever the stress applied, it is directly proportional to the shear rate. Okay, but it happens only after the yield value. So plastic systems will show yield value. Yield value is nothing but stress that is required to break the flock-lated systems into individual particles. Okay, right. So another important thing to note here is 10 to 30%. So here that is also important. Less than 10%, you can see that there is no flux form. If it is more than 30%, also it is not affected. The 10 to 30% concentration is important to exhibit this plastic flow. Right? The concentration is very less, or the concentration is more than 30%. We cannot see this plastic flow. Right? So the flock-latex suspension will act as a plastic system when it is between 10 to 30%. And the characteristics of the diagram are, it shows yield value. So yield value is nothing but the stress required to convert aggregated floccules into individual particles. Right? Second thing, diagram does not pass through the origin. It means that the changes are not spontaneous. What is the change here? Decrease in the viscosity. When apply force, it starts to flow. So decrease in viscosity is not spontaneous. It becomes spontaneous only after the yield value. So the important point to be noted here is yield value is can be determined from this diagram, and that yield value is a measurement of degree of flocculation. Degree of flocculation, flock-latex suspension. Stability of the flock-latex suspension depends upon degree of flocculation. More the degree of flocculation, more the stability. The flock-latex suspension will be more stable if it's having very good degree of flocculation. So, how to measure the degree of flocculation? There is one indirect method of measuring the degree of flocculation is by determining the yield value, because yield value is nothing but force required to break the flocks. If the flocks are very strong, then we need more force, more stress, right? So more the yield value. So yield value is a direct indication of degree of flocculation. Thereby, we can check or we can measure the stability of flock-latex suspensions. Okay. So plastic systems are Bingham bodies. An example for plastic systems are 10 to 30% flock-latex suspension. The diagrams shows that it's a curve and not a straight line, and it shows the yield value. Yield value is the stress required to break the flock-latex particles into individual particles, and yield value is a measurement of degree of flocculation. Second thing is, it does not pass through the origin, and it is not spontaneous. The changes are not spontaneous. So remember here, when you apply stress, the viscosity of the substance decreases. Yes, flock-latex suspension. If you take it, shake the flock-latex suspension, what happens? It becomes easy to flow. The fluidity of the substance increases. Right? Next, pseudoplastic system. So far we have seen two diagrams, and I think and I believe, okay, if it is interactive class, I may be having some volunteers to explain this diagram. Right, okay. So I believe that you will be in a comfortable position to explain the diagram for this particular type of system, right? Okay, so what are the points we are observing here? Yes, what's the first point? It is a curve, right? So the diagram shows a curve. That means stress and strain are not directly proportional, right? If you are able to say this point, yes, I appreciate you. Take a bow for your sharpness. Okay. So first point is it's a curve, which means that the shearing stress and rate of shear are not directly proportional. Right. Second point, the line passed through the origin. Okay, the line passed through the origin. So that means what? The changes are spontaneous. What is the change? If you change the rate of shear or you apply the stress, the viscosity will decrease. It's the change. Okay. So once you change the stress or rate of shear, liquid viscosity decreases immediately, but the decrease is not directly proportional. That's the point. Okay. Now, diagram is saying all these things. Now take an example and apply it to have a better understanding. So what is the example given here? Polymers in solution. So that's an example for pseudoplastic system. So polymers, as the name says, polymonomers. So polymonomers are called as polymers. So here, like flocks is a very small group. So polymers is a very large aggregation. So more number of monomers are grouped and they are merged to form a polymer either by physical reaction or chemical reaction. That is a polymer, right? So we are taking the polymers, then solution, polymer in solution, dissolve it in water or disperse into a solution. Okay, right. So what's happening there? So when you observe that, all the monomers will be moving in all possible directions. It will be moving in all possible directions, right? So when it's moving in all possible directions, it is not possible for the solution to flow. Okay. So once you apply the stress or shake it, rate of shear, what happens? The monomers will be realigned towards the direction of flow. So from different directions, it will be aligned towards the direction of flow. For this to happen, continuous amount of shearing stress is taken by the monomers. Okay, so that's the reason why here you have a continuous change in the shear stress. Okay, so it is not directly proportional. Why? Because when you apply 10% of shearing stress, it is not producing 10% change in the rate of shear. Okay, it is producing only 7%. The next remaining 3%, what happened? That 3% of the stress is consumed by these monomers to realign into the direction of the flow. When you stop applying the stress, what happens? The monomers again will go in different direction. The flow stops. Okay, so there will be a flow only when you are applying the stress, right? And all the stress is not directly seen as a flow. Considerable amount of stress is continuously consumed by the monomers for doing the realignment. That's the reason why polymers in solution is not showing a directional flow. It's having a curve and the flow is continuous. But the flow is spontaneous, but it is not directly proportional. Okay. The pseudoplastic system example is polymers in solution. The characteristic things are is having a curve that the change in shearing stress and rate of shears are not directly proportional. It does pass through the origin and the spontaneous changes are spontaneous. Okay. Right. So in plastic system and pseudoplastic system, both the rheograms, we observe one thing: the curve is coming below the plane. Okay, when you try a straight line, you can see the curve is coming below the plane. What does it mean? The rate of shear decreases. When the rate of shear decreases, the resistance falls, viscosity increases. Okay, so rate of shear is decreased. So we call this a shear thinning system. Pseudoplastic and plastic systems are called a shear thinning system. It means that on changing the shearing stress or rate of shear, what happens? The viscosity decreases. Okay, right. So we move on to the third part, that is dilatant system. So dilatant system, okay, start interpreting the rheogram. Right. So first thing is it's a curve. So it's very clear indication that shearing stress and rate of shear are not directly proportional. Okay. But the change here is, yes, the curve is above the plane. The curve is above the plane. Right. So we know that if the curve is below the plane, on changing the shearing stress or rate of shear, the viscosity will decrease. But here, the curve is above the plane, which means reverse phenomena. So when you change the stress or rate of shear, the viscosity increases. Okay, so it is a shear thickening system. Thickening is increasing. So whereas plastic and pseudoplastic is shear thinning system, here this is shear thickening system. Okay, right. Second thing, the line passed through the origin. So it means the changes are spontaneous. So whatever the change, whether viscosity is increasing or decreasing, here it is increasing. The viscosity is increasing, it is immediate, it is spontaneous. Once there is change in the stress or rate of shear, the viscosity starts to increase. Okay, right. So why it happens? We'll see an example. So example for dilatant systems are deflocculated suspension having more than 50% of solids. So here the point is very important here. Deflocculated. Okay, what do you mean deflocculated? Individual particles. There is no flux. There is no force of attraction. All the Suspension means solids dispersed in liquid. The dispersed phase is solid and the dispersion medium is liquid. So the solids are individual. It means it takes more time to settle, but once it settles, it forms a hard cake. It cannot be removed. Okay, that's a deflocted suspension. So deflocted suspension having more than 50% of the solid. So you have to note that catchy point here. More than 50% of solids. That means the liquid content is less and the solid content is more. So whenever you have a system where the liquid content is less and solid content is more, it will show dilatant. Dilatant means on applying or changing the rate of shear or shearing stress, viscosity starts to increase, right? Another well-known example is beach sand. Okay, you might observe it when you stand in the wave. If you are standing and the wave goes back, you feel that the sand below your foot is eroding. You are losing your grip, right? Whereas when you start running on the beach sand, okay, instead of feeling a loosey sand, you will see that the sand gets harder, right? So at ideal condition, the sand is very loosely packed, right? Whereas when you apply stress, how the stress is applied? By running over it. When you are running over it, stress is applied on the sand. So instead of decreasing the viscosity starts to increase. When the viscosity increases, the sand becomes tight, right? That's the reason why when you run on the beach, it's very hard, whereas when you are standing on the beach sand, it is very loose. A very typical example for dilatant is beach sand. Okay, very rarely pharmaceutical systems will be showing dilatant, and it is not preferred to have a dilatant system in pharmaceuticals because, for example, if you have a cream which is showing this type of behavior, right? When you apply stress, viscosity increases. So when you are going to stir, when you are trying to mix or stir the cream, stress is applied, right? When you apply a stress, then what happens? If it starts increasing viscosity, it becomes difficult, right? So dilatant system is not preferred for pharmaceuticals. Okay, right. The mechanism of dilatant system, right? As we have discussed here, generally defloculated suspension having more than 50% of solid will be looking like this. More solids and less liquids. They are closely packed, minimum wide volume, sufficient vehicles. On applying stress or changing the shear rate, what happens? The solid particles goes to open packing. When it goes to open packing, the liquids are not sufficient to cover the solids. So it fails to lubricate the solids. Because of that, friction increases. When friction increases, resistance to flow increases. Resistance to flow is nothing but viscosity. So viscosity increases. So this is the phenomena which makes dilatant systems to show increase in viscosity, whereas plastic and pseudoplastic shows decrease in viscosity. Right. So I think I have given notable explanations for Newtonian and non-Newtonian system. So I'll fail in my duty if I don't give credit to this person, Alfred Martin. So all the content, whatever I have taken, is now taken from his book, Martin's Physical Pharmacy and Pharmaceutical Science. So the credit for this class goes to this person and his excellent and splendid work. Okay. So let us summarize what all things we have seen today. So we have seen what is rheology and how it came into existence. It came into existence 1929, and it is explained by Marcus Rayner and Eugene Cook Bentham. Then William Scott Blair applied it in pharmaceuticals. The rheology is basically on stress and strain. Stress and strain, very simple example, you can say we lecturers, whatever the task we give, for example, write an assignment is the stress, right? So if you ask the student to write assignment, that is a stress. Now what the student will do, either he will write it or he will take leave on the day of submission. That is the strain. The response of the student is the strain, and the task given by the lecturer is the stress. So rheology is all about stress and strain. So stress, there are two types of stress, tensile stress and shear stress. So our point of interest is shear stress. Shear stress is nothing but force applied parallel to the object, and shearing stress is always directly proportional to the strain. Okay, then for studying the rheological property, we should have rheogram. So rheogram is nothing but a curve, shows relationship between shearing stress and shear rate in all applications, solids, liquids, semi-solids, everything is important. I mean, rheological property of all the solids, liquids, and semi-solids are important. Then classifications, Newtonian rheograms here studied, straight line, directly proportional, single value is enough to define. That single value is called as coefficient of viscosity. And those who don't obey the plastic system, example for Newtonian is water. Okay, so very well known example is water. And majority of the systems do not obey the Newton's law of flow. So plastic systems, examples 10 to 30% of block weighted suspension. Here curve is applied. I mean, yield value is present. Yield value is a measurement of degree of flocculation. Yield value is nothing but the stress required to break the agglomerate, flocculated follicles into individual particles. And the viscosity expression is given as eta equals to F minus small f by G. F denotes the shearing stress and small f is the yield value. Okay. Then a pseudoplastic system, examples polymer in solution. Here also same thing. It's a curve and it passes through the origin, and small considerable continuous and considerable amount of stress is taken by the monomer follicles to align towards the direction of flow. Then dilatants, it's a shear thickening system. So when you apply the change in stress or rate of shear, viscosity increases, and that is due to open packing and less volume, less liquid content. Okay, right. So thanks for joining this class, and I hope it is beneficial for you. So if you need of any topics to be explained, you can put it in the comment section. Surely I will try to help you all in that. All right. Thank you all for joining.